Hi folks, thanks for joining us. This is a Unix tutorial as part of the Bioinformatics Virtual Coordination Network, looking at how to start from scratch if you've never worked in Unix before, and learning some of the basics that will make it easier for you to, one, do Unix on your own going forward, and two, use Unix as part of the BVCN lessons as we're going, as the pandemic continues onwards and quarantine continues to happen. We are going to be working through the Unix crash course that has been created by Dr. Mike Lee at NASA and in the Happy Belly Bioinformatics workflow. This is the webpage up here. I'm not going to try and read it out to you, but I will post it in the description below of the YouTube video. This will bring you to the Unix crash course, which gives you just a very quick overview of why we're learning Unix in the first place. And I'm assuming that if you're here, you might get an understanding of why that's the case. The reason we're learning Unix is because this is the foundation for many ways of dealing with computational data that in large volumes, and also in a way to make sure that the things that we're doing are reproducible. And the thing that I think always trips people up quite a bit is that it's the non-graphical user interface version of everything that you kind of hold dear when you're used to working in an operating system, be it Windows or a Mac operating system. And so a lot of the things that you'll see have analogs in those instances where you normally use a mouse and a keyboard to get to. But in this instance, we'll only be using the keyboard. And hopefully you'll see that one of the benefits to all of this is that a lot of the tasks that you may have been doing by hand, especially as file numbers get large or file sizes get large, you can actually do very quickly just using Unix without ever having to use any bioinformatics tools or anything like that, just the strength of Unix alone. So that we're going to get started. We're going to follow along here on this number one, follow the link. And so the initial setup of what we're going to do here, we're going to do all of this all of this exercise through Binder. I'm going to talk a couple minutes about Binder, just so you are aware of what it is. So it's this incredibly powerful tool that is open source and has been generated for folks like us, but not just us, but everybody, that allows us to take GitHub, which is a repository that people generally use for code and coding-like environments. And it allows us to take, with a little bit of extra planning, take an entire, what is called a repository in GitHub, and basically launch it in its own computational environment. Now, these are small computational environments. There's a limit to how much memory you can use. There's a limit to how much data you can put there. But it allows us to do something that is sometimes really hard to do, which is ensure, one, that everybody here is working in the same environment, and we don't have to worry about instances of your computer not working the way that my computer works or the next person's computer works. Two, it runs in your browser, so we don't have to do any fancy installs that would make it problematic. And three, and there is a three, if I can remember what it is that it allows us this ability to, as we go forward and you become more skilled in this, you can share your data in a way that is completely reproducible. So you can then give people, through Binder, a step-by-step flow of how you processed your data. It might not be the full data because, like I said, it's limited, but you can include code that you've written, you can include steps that you have written, and you can include components that maybe haven't been fully fleshed out before, and allow everybody access to that type of information. So the thing that we can do here is we're going to click this. When we're working with Binder, the links that go along with this are a pretty hot mess. But if we click on this button right here, it'll launch our Binder for everybody. So Binder then takes a moment to build the environment that we're working in. So the way this works is a couple limitations that go along with this. Every time you start up a Binder, that instance is live for about 6 hours. And that if somebody else has used the Binder within that 6 hours, it actually loads up a little faster than when you're doing it for the first time. The load up speed is also dependent on how big the environment is, right? So the things that you're asking it to install, it's installing every time you start up the Binder. So it can take a little bit longer if there are more tools involved or things like that. The other thing is that there are 3 major hubs for Binder. So one of the downsides is that I came in about 15 minutes before the start of the lesson, and I clicked Binder to make sure that it had been loaded recently. So you saw it started up pretty quickly there. Unfortunately, if somebody else was in one of the other 2 major regions of Binder, Europe and Asia, what would happen if they clicked it and it had been the first time, that startup time might have taken maybe twice as long or 3 times as long than what you just saw here. So if it takes a little bit of time, don't worry, it's okay, you haven't done anything wrong, that's just how Binder works. So we're gonna be using, I'm gonna break this out over here. Nope, don't wanna join the other screen. Just gonna share it a little bit like this, try and have it as a dual screen scenario so that I can code on one side and then have the example on the other. It really wants me to join. Now it's too small. There we go. Perfect. Right. And so the thing that we're going to do to all of this extra time and effort to go into this is we're going to use the shared terminal environment that's part of the Binder. So it's right here. It's going to be this button that we're going to click. When we do, it's going to start up a terminal for us. And this terminal is going to be the same for everybody who does this tutorial. And it'll be the same for everybody who's doing it live along with me. Now this is the big if here, if you really, really, really feel compelled to use this on your own computer and not use the Binder environment, there are 2 things that you need to do. The first is to visit our wiki page here as part of the biovcnnet.github.io page, where we have in our wiki this step 1. Notice that it's completely numbered differently than everything else in our wiki page, which is how to set up a Linux or Unix environment on your own computer. And this lays out ways that you can do that on a Mac and a Windows, including multiple options on the Windows, depending on if you're using Windows 10 or an older Windows version. And so you can follow along these steps if you wanted to make sure you have Unix or Linux available on your own computer. And then if that was what you were doing and that's what you felt comfortable with, you would blindly copy this information right here to make sure that you got, and you could just copy and paste each of these lines one by one to make sure that you then had the data that we're all going to be working with on your computer in an environment that mirrors what we're going to be working with. If you then ran this and you got an error when you run this curl step, I would highly recommend just moving to the Binder right now. We're not going to troubleshoot that right now. The cure to this solution would be making sure that Ruby is correctly installed on your computer, but we can come back to that in the future. Okay, some things that we should do talk about before we get started. Mike has named these foundational rules of Unix. Foundational rules, here we go. So the thing that, the 3 points that he's laid out here is the first is that spaces are important. And I'd like to emphasize here that not only spaces are important, but typing correctly is important. Typos lead to errors because the computer doesn't know what you're doing. There's no autocorrect in a lot of Unix environments. So if you're typing something and you transpose elements, the computer's not gonna be computer won't know what program you're working with. The same works for spaces. So normally spaces are the character that the computer is looking for to understand where there are breaks between arguments. And so in this example here, normally, you see this a lot with people who do not work in these types of environments. You might write a file name with a space in it. Of course you will, right? Like it makes sense. That's how you look for information. Normally, you look for spaces to tell you where there's a difference between one word and another. It's gonna not end well if you do that in the Unix environments while you're naming your files. So some common ways that you can get around that is you can use the underscore or the dash to get around that and still provide a space to make it easier to read, but at the same time make it easy to read for the computer. So that's the first thing to cover. The second, the general syntax that we're gonna follow along with is that normally we're gonna write something like a command, which is gonna be our first element of what we write. There's gonna be a space, and then we're going to probably put in an argument. And an argument can be a number of things, which are listed down here, which may include parameters or options, also commonly known as flags, that are part of the Unix system and the Unix commands, but then also any file or folder or directory that we're trying to point to as well as we're going forward. Great. So let's do it. Let's run our first command. It's going to be nice and fun and straightforward, and it's going to be the date command. So if we all move over to our terminal window and just type in the word date, again, make sure that you type it correctly, otherwise it will throw an error. You hit enter, and surprise, it gives us the date. It gives us the local time and date of where you are, where your computer system is set. If we wanted to, we can use this -u, which is a flag, right? So it's an option that we're telling date to use so that it's going to do something different. And so if we do date and put a space and then -u and hit that, so now it's not giving me the time locally, it's giving me the time of the universal Greenwich Mean Time, UTC. And so you can see there's a difference there. Now Mike wants us to go through a number of different examples of how not to do this correctly and to see what happens. So if we do date space u without the dash, the computer doesn't know how to interpret that. The u needs that dash to let it know that it's a flag. And by typing it without it, now date is looking at this thing and going, I know you're trying to do something here, but it is not something that I recognize what you're trying to do. And so it throws this error for us that says data invalid date u. That's a good point. U is not a date. The other thing that we can do is we can miss the space and try to type it like this, and we'll probably get a different error. And in this error, it specifically says that date-u is not found. And that's because it thinks it's a command, right? So it's looking in the computer for a program or a script or a command that's called date-u, which doesn't exist because it's not a real thing. So the next commonly used tool, Unix tool that we'll be using is this tool head. And so head prints the first 10 lines of a file. So we're going to do head, and then we'll do example.txt. Now when I hit enter, very nicely in example, it just counts up for us so that we can know for a fact of how many lines are being printed. And so head normally prints the first 10 lines of the command that of the file that we're looking at, right? And so this is an important part here. So we were talking before about commands. We wanted to talk about commands and arguments. So here the command is head, and then because head needs to look into a file, we need to give it the name of the file. So that's a required argument that we're going to pass along to that. If we just ran head by itself, which we can do, right now nothing happens. So head is trying to look into a file, but we didn't give it a file name. So now it's just looking forever, which is not good. We don't want to do that for too long because it will do it forever. So we can stop that, as we can stop most commands in Unix using, you're going to hold down Control and then type C. And you'll see this little $C that pops up, and that's saying that the command was canceled. And I've now hit it a couple times because it didn't respond right away, but that will cancel out the command that we're working with. It might be different on a PC if you're using a PC, not the control button, but probably the option button or the command button, whichever one is the one that you're working with. So you can play around, and it might be different for different keyboard settings on Windows. Okay, so we have the command and we have the argument, but now we can add multiple arguments into this setup. And so what we're going to do is head, again, normally prints the first 10 lines, but we're going to now tell head how many lines we actually want printed. And so we can do that by doing head-n, n for number, 5. And so we're going to print the first 5 lines instead of the first 10 lines, and then we'll do example.text. And you can see, instead of printing the first 10 lines, we've now printed the first 5 lines. Okay, so how do we know what types of options or flags are available in our commands? So there are a couple ways of doing that. One of them is this help command that exists that several tools will use. So if you use head-h or head-help, spell it all the way out, let's do the head-help. it prints out all of the information that we might want and what the different flags are. So here it's telling us that normally the usage format of this is that you use the command head. There's some option here, and these are the options down here. We'll talk about those in a second. And then the file that we want it to run on. So normally, head will just print the first 10 lines of each file in the standard output. If there's more than one file, it goes through and prints the first 10 lines for each of those files, giving you a header information of the file that it's printing from. So you can print from multiple files if you wanted to. And then here are the options that we can work with here. So we've used -n, which is the number of lines. We can also split this by the number of bytes, which is a very interesting way of thinking about of files, right? So if the file is 10 kilobytes in size, we can split this up in 1 kilobyte chunks. Would we want to do that? Not necessarily for this file, but in other files, you might be able to envision a way of doing that. There are these other elements here, including making sure that the output is silent. So never print the header lines. If you're giving multiple files here, this would prevent them those header lines from being printed, as opposed to -v, which explicitly commands it to be verbose, and will have it print out all the lines it can as it goes through it. And then -z, hit a zero terminated. Line delimiter is null, not a new line. That gets very specific into what we're trying to do there. We'll just glass over that right now. So this is an important part, is that a lot of these commands have this underlying information that's part of them, not just in Unix, but especially in when you get into tools that you might be using in the future. And so this bold is pretty important here, and is really an important part of this, which is the fact that it's important to become familiar with the rules, but it's not essential that you memorize everything. You don't need to memorize all of the commands. You don't memorize all of the options. There's a lot of ways that you can get access to that information, including these help commands that are built into the tools. So let's talk a little bit about the Unix way the system is set up. And so this gets into the heart of that part that I was talking about, where intrinsically we kind of understand, as you know, we've now been working around computers, a lot of us, for the better part of 30 years, is that there's a structure that happens in our operating system, right? We click on folders, and that folder opens up another folder, and then then there might be a folder inside there, and we can go further down until we get to the files that we want to open, and then we click those files specifically. It's exactly the same setup in Unix, except that we are keeping track of that information as we go. We can ask the computer for help as we go to make sure that we know where we are, and that's what we're going to talk about in a second. But we are stepping up through what is known as the path to where the location of a file is. So root is normally a directory that you might not spend a lot of time in. This is where everything starts for the computer. This is where all the startup information is. These are where these Unix commands live. This is where everything, the whole kitchen sink resides. And then in root, there might be a number of different directories or folders, and you can see them here: applications, library, users, right? So this is mirroring very similarly to what you would see on a Mac situation. We can then go into users. We can see there's a user named Sam. This is generally defined as the home location, which we'll talk about in the situation. So there's the root, which is the base of the computer, and then the home, which is normally set for the user specifically. And so those are two different spots. You normally will download automatically, almost without thinking about it, when your computer's set up. You would download to the home directory just by default. And then we might go here from our home into documents, and in documents is where all of this information reside. And so if we were to write out that full length all the way from root to user to Sam to documents to the name of the file, that's something that that's our path. It's the location of the file is present, and it's giving us our absolute location of where we are from the file. A file in relation to all the other files in the computer. We can also do that as an absolute path from our home directory. We use the little tilde here to denote where our home directory, what our home directory is. So if you did this on your own computer, one of the first commands that you would have done that was recommended to you as part of this tutorial was you typed in cd tilde, which would have taken you to your home directory by default. So again, the root is where you start. That's where the computer starts. Home is where you, the user, normally starts. And we can do lots of things to track where we are on our computer. And so the first command that can be very useful, and I'm going to do some stuff here to make it easier to maybe see, so it's not at the bottom of the screen. You do not have to do that. I use the command clear to clear the terminal so we can look at it from the top. So the first command we're going to look at here is pwd, which stands for print working directory. So if we hit pwd and hit enter, this is where we are. So we see home, which is the start of our path, some directory called javyan, and then some directory called Unix intro. And Unix intro is the part that is part of this this tutorial that we booted up in the binder. We can also ask, well, what else is in this directory that we're in? You know, we know where we are. We're in this place that we printed out. What's actually here? What files are here? What folders? What directories are present? And so you can type ls, and that will print everything that is present here. And so they're currently colored because that's how Binder does it. It might not color it on your computer, and it might color it a different color. But here, what it's breaking down is in blue are the directories that we have present here, and in black is our example.txt file that we were working with. So we're going to talk about working with this example.txt, both using our absolute path, which is the one that we've been talking about, where we're writing out the full location. And so we can do this, So we can do this all the way from root, or we can do this from our home location using the tilde if this is part of the path that we're in. So this works if the directory that you're working in is under that home directory. If for some reason you've put it somewhere else, you would have to go through the path that would lead you there, right? So the best way to do that would be starting from root. But in most instances, this will be the case. And for the example, that's what we're going to do here. Right. So we did head, and we can run head again on our example.txt. And that prints out our first 10 lines. So what we've done here is actually just said, hey, you know, based on where we are relative to where I'm typing right now in our current directory schema, if there's a file named example.txt, please print the first 10 lines. So that works because that's where we are currently, but we can always get to where the file is using its absolute path. So in this instance, we're going to do tilde home, and then, sorry, not tilde home, tilde Unix intro example.txt. So again, this is going to print out the exact same thing. We're telling it to do exactly the same thing, but instead of telling it, hey, if there's a file that happens to be named here, we're saying, no, we know that there's a file named example.txt, and if you follow this series of directories to get to it, that's where it'll be, and you'll be able to run head. And so this is just helpful in lots of ways, because it allows us, and we're going to do that in the next step, it allows us to target components that are elsewhere on the computer, both when we know exactly where it is and also where it is relative to where we are right now. So in this instance right now, what we're going to do is we're going to use head. We just use head on our example.txt. Now we're going to try and use head on the word, or on the file notes.txt. So we're going to do head notes.txt. And so I think if you're looking at this, you might guess. So if I just said this is the contents of the directory that we're working in, you can see that there's nothing called notes.txt. So when we hit enter, you'll see that it says that there's nothing to open. That's because the file's not here right now. And so, you know, if we ran less, again, you can see that that's the case. There's no file named notes. So, okay, so that's interesting. Why would we be doing this? The reason we're doing this is because we can use all of this information to not only look at the contents of a directory from somewhere else, but we can also use a Unix command to target files in those other directories. So in this case, we're going to do less, and we're going to use the directory called experiment that's in the directory we're current in, and we're going to take a look at the contents that are inside that. And if we look there, we can see that there is a file called notes. And so now that we know that that's there, we can use the relative path of where we're working right now. We can ask the computer, hey, we're working here right now. Can you please look at this directory that's right here, and then the file that's inside that directory, and print out the first 10 lines for me. And so we can ask it to do that. We can do experiment, and then we're going to put a slash here. So that / indicates that this is a directory that we're working in, or that we're looking for, right? So it's not a file, it's a directory. So we're saying head, look into this directory, and then we can say notes.txt. Oh, and look what it says. First I did this, then I did that, then I had to start all over again. And that just seems like a very interesting way of looking at life. And so this allows us, you saw that I was typing those out, but we knew what the contents of all this information was, right? One of the nice things about Unix is this tab completion that occurs that's built into the system as part of the overall Unix, the way that Unix works. And so the way this works is I can start typing and do something like this where I have head. And the example that Mike uses here is that if we type in an E, it and hit tab. So I just typed in head, E, tab. It goes EX. Okay, well, that's interesting. Why would it go EX? Well, because what it's trying to do is take that E as the starting character and complete any name of a file that has an E at the starting point. And so in our example, we have two elements in our directory that we're working with that start with E, example.txt and experiment.txt. So when we hit tab, it completed it as much as it possibly could, which is that X shared between example and experiment. If we tab multiple times here, it'll actually print those options off for us. And so you can imagine if this was a pretty busy directory, we could do this and print off and see exactly what the files were for the starting components that we were interested in. And then if I were to type an A here for the examples and hit tab, you'll see this, completely auto-completes the rest of the word, right? And so head or tab completion allows the computer to help guide you where files are in your system, right? It allows you to basically let the computer say, okay, I think that there's a file named X here. Let me start typing it. If I hit tab and nothing comes up, it might mean that I'm in the wrong directory. It might mean that that file has been misnamed incorrectly. So you might think it says example, but you might have mistyped and it might say EAXMPLE. And so this is just a way to make sure that you can skip that part where there is no autocorrect, right? Sometimes file names can get very long. And if you're using tab, you can get to that point of getting the exact file that you want without necessarily having to expect to remember everything that you're working with. And so we can use this. Let me show you this on a full scale here. So we can do head, EX, double tap. There are two options here, example.txt and experiment. We can say experiment. So now if we just put a P here and hit tab, that'll autocomplete for us, including giving us that / to indicate that it's a directory. And now we can type an N and hit tab, and it'll autocomplete that notes name file for us. So if we hit enter, it'll pop up like that and give us exactly what it gave us before when we were looking at the notes.txt. And so you'll see me probably going forward now using that tab command to move through the command, type out these commands a little faster. And that you should do that as well and practice doing that because it's a good way to make sure that, again, like I said, you're using the right file names, and it helps you in time and keeping your sanity as you go around. And so the last thing that we're going to do is we're going to learn a command called cd, which is short for change directory. And so this is actually going to virtually move us from the directory that we're working in into other directories. And so we can do that right now by doing cd. And so you're going to see me tab complete, experiment. And so now when I hit enter, you can see that this information changed. We've added an extra layer here. When we run pwd, it's now increased in length. So now we're in home, Javian, intro, Unix intro, and now we're in the experiment directory. And now when we hit ls, so instead of hitting ls and getting these outputs, we're going to hit ls, and we'll see that notes.txt command. And so we can do a number of things here. We can move around to lots of other directories on the computer. We can go back to our starting directory using our absolute path, Unix_intro. That takes us back up one level to where we started and where we can hang out. I'm going to move back into experiment. And we can also move up using a shortcut here. That's a default shortcut that's part of Unix. So in Unix, there's a lot of shortcuts that you'll see as we're going along. This double dot, so tells the computer to look one level above where you're sitting right now. So I can hit CD double dot and hit enter and step back one level. And so you can see that I went from experiment into Unix intro and moved back one level. If I hit PWD, you'll see that information reflected. And now when I hit LS, you'll see the first four files first set of 4 directories and files in the Unix intro, then compared to where we were in experiment. And so we can use this pretty regularly, and we will in the examples going forward. And we can use that information. We can use the double dots. We can use our absolute path. We can use our relative path to get to where we need to be to do our various components. And so just to summarize what we've gone through here, we've talked about how our path works. We've talked about the difference between root and home, and then the difference between an absolute path, which may start at root or may start at home, versus a relative path, is where we are relative to where we are right now in the directories, and then how tab completion works. And then these are the commands that we went through, including date, head, pwd, ls for listing, and cd for changing directory. And then information that goes along like this. The special characters that we learned include using a / with nothing else to get to the root directory, a tilde / to get into our home directory, and then using this dot. In this case, we've added a component to say we're stepping up through a directory, this dot to move up one directory at a time. And you'll see in the future lessons that we can start stringing a lot of these elements together. So the dot takes us up one step, but why only do one step when you can do multiple steps at a time? And so we'll see that as we're going forward. And that'll be lesson 1. Please come back for lesson 2, where we will be talking about working with files and directories. Thanks very much.